I'm always a little bit concerned about what it is that you remember and what it is that you don't. But I want to focus our conversation today on energy. And I want to do so by reminding you that we have developed a pretty extensive amount of information surrounding energy, but that when we first started talking about energy, we were talking about kinetic energy. And that one's probably the easiest one to deal with because any form of motion is going to have kinetic energy. So we've kind of formalized it into two formulas, but remember, it's about any kind of motion. Any motion that exists means that you have kinetic energy. Now, things that can be directly measured either because something's moving or because we can calculate the amount of work done. Now, I want to remind you about where a couple of things came from because it's not going to make a lot of sense until we kind of see it here. So one of the things that I do want to remind you about is that we did talk about how much work it would take to lift somebody from the ground to some place above the ground. And when we did that, we calculated the work, stating that this was our reference level, and we're going to move the person to a new point in space above the reference level. And this was by direct calculation of work. Now, calculating work is an integral, and the reason it's an integral is because we talk about how much force is required to change an object from one place to another. The dx here represents a small change in position. The dot product is telling you how much of the force is in the direction of the displacement, and F represents the size of the force acting on the object. So if we are dealing with a situation in which the force is constant, we don't have to integrate. So if I'm just lifting something near the surface of the Earth, the force acting on the object the entire time is the force of gravity, mg, acting downwards. But the direction that we're lifting is upwards, so each small change in position, dx, is in the upwards direction. So we're talking about moving something from the reference level, h naught, to some place above that. We're moving upwards, small increments at a time, and calculating how much total work is done. In fact, it would look like this. We'd have the integral from h naught to h of mg dot dx. Now the dot product, if you'll recall, produces a cosine. It tells us how much of your force is in the direction of motion. For this example, the amount of force acting on our object is just mg, but dx is upwards, while mg is downwards. So if I want to evaluate the cross product, I'm going to put this cosine of 180 degrees in there because the direction of the force compared to the direction of the displacement is 180 degrees. Now this isn't an integral that we really have to do very much. In fact, if you'll recall, we didn't do the integral at all. We used a different version of work. We dealt with work from a constant force, but we're not going to be able to stay secure in that world anymore. So we're going to do the full thing here and show how this was calculated. mg doesn't have anything to do with x, but when you're dealing with an integral, the integral bracket tells you that you're going to be taking the antiderivative. That's what that little fancy s is. It's bracketed by the integrand. This is the part in the middle. And the dx is telling you what the important variable is. In this case, the important variable is x, which is not featured anywhere in the integrand. The integrand has two constants, the mass of the object we're lifting and the acceleration due to gravity, which are both the same near the surface of the Earth. So for this particular integral, mg can come out front because it never changes. And since cosine 180 is just -1, I'll just pull my negative out too, because it's a constant. It's true for every term. But now we have to integrate what appears to be nothing with respect to x. But it's not nothing. What is it actually? X to the 0 power. That's right. So we're going to use the polynomial property here to do our antiderivative. And this shouldn't be too tough for you guys. The polynomial one says to take the exponent and add 1 to the exponent and divide by the new exponent. So I'll take x to the 0 power and make it x to the 1 power and divide by 1. Now that's just taking the antiderivative. I still need to bracket the fact that I have my limits of integration, because when we do an integral, it's more than just the antiderivative. The integral also has our limits. So we place in our top limit and subtract when replacing our bottom limit. And this is how much work is done lifting something. The work is negative, and that's not accidental. We defined it this way because we said that any change in potential energy is equal to minus the work done against a conservative force. This was the work done against a conservative force, so the actual change in potential energy is minus this value, which is how we get mg h minus h naught. That's how potential energy works. We say how much potential energy we have is minus the work done by your force. All right, so far? All right. Now, all that does for our conversation here is give us a way of expressing gravitational potential energy. And I wanted to do that just as a reminder of where this comes from. And we're going to do this twice because I think you need to see it twice. So there was another form of energy we had too. What was the other form of potential energy? Elastic potential energy. Elastic potential energy brings us to a more interesting dilemma. Because if we're dealing with elastic potential energy, then we're dealing with a situation in which the force isn't constant as we move from one place to another. Right? If we're going to try and compress a spring, the force from a spring is proportional to how much you compress it. So the more you push on the spring, the more force that's required to compress it further. Or pull out a spring. It doesn't matter which direction we go, but if we're going to say move the spring in this direction, the force required gets bigger and bigger. The minus sign is already here. This is something that helps us with the dot product, really. That minus sign is telling you that if you move the spring to the left, the force you're going to get from the spring is to the right. And if you pull the spring to the right, the force you get from the spring is to the left. It's telling you, based on Hooke's law, that the force is in the opposite direction of the displacement. That puts a permanent minus sign in our expression for the work done here, if we're talking about the work done by the spring. So let's calculate the work done by the spring. Let's say we're going to move the spring from 0 to some location x. Well, the work done is going to be F dot dx for the spring. Now this is going to be a little bit more spicy because for this particular one, we're going to sub in minus kx for the force. Our force does have something to do with position. It changes. So we actually have a integrand that has something to do with our integrating variable. Now there's things that are still constant here. K is a constant. It's something that has to do with the spring. So K will be the same for every term. And the negative sign will be there for every term. So like in any other integration setup, any variables that have nothing to do with your integrating variable become constants for the purpose of your integration. So minus k comes outside the integral, but we're left with having to take the integral of x with respect to x. I dropped the dot product because the negative sign was inherent in Hooke's law. It already indicated that we'd have a negative sign. So that's why I didn't talk about evaluating the dot product. We know the force is going to oppose the direction of motion. But now we have to do the integral here. Again, it's just a polynomial, and we'll use the polynomial rule. This is x to the what power? X to the 1 power. So if I want to evaluate the integral, I do the antiderivative first, which means x to the 1 plus 1 power, or x to the 2 power, divide by my new exponent, which is 2, and then evaluate this from 0 to x. There's not much to do here, but again, it produces minus 1/2 kx squared. That's the work done in compressing or elongating a spring. That's not the potential energy, but the potential energy is minus the work done. which is why the potential energy works out to be positive. You can press a spring, you store energy in the spring. Yep.
Wait, could you give me a little more clarification on what you mean by minus the work done? Like, what is it subtracting?
You're not subtracting anything. The definition of potential energy, the change in potential energy equals minus the work done by a conservative force. It's a definition.
Oh,
Okay? So that's how we define potential energy.
got it. Thank you.
Is that okay?
Yep.
All right. Now, this brings us back here, where we have two different values, or two different ways of calculating potential energy. One for springs, one for gravity, and this is where they came from. But there's a problem with this. And the problem has to do with gravitational potential energy. Gravitational potential energy is kind of a misnomer. We are talking about something that is only useful in a very narrow set of circumstances. And that's a set of circumstances where G is constant. But G is constant only near the surface of a very large object like the Earth or the Moon or another planet. Everywhere else in space, the force of gravity changes depending on how far away from the object you are. If we really want to talk about how much energy there is when it comes to gravity, we're probably going to have to reform our thinking around how we deal with gravity. Because the potential energy we've been using works great if you're talking about going down a slide or a roller coaster or comparing two things that are relatively close to each other because you're near the surface of the planet. But if you want to say, go to the moon, well, how do we compare the amount of energy that you would have to get to the moon with how much energy you have on the Earth? Right? We can't assume the force of gravity is going to be the same everywhere between the Earth and the moon. So figuring out the amount of energy difference or the amount of energy required to get there can't be done using MGH because the force is going to be changing the whole time. In fact, how will we compare the relative amount of potential energy you have, say, here with the relative amount of potential energy you would have there? The only way that would work is if we could find a point of reference between both of them. And currently, trying to use the surface of the Earth won't work. That's not a convenient point of reference. Now, I'm going to be point forward when we talk about energy, we want to find a reference place that can be used for both the Earth and any other place we wish to go in our solar system or in our galaxy or in our universe. So what we say is we are going to choose a reference point that is, make that small, infinitely far away from any of the things we wish to be near. So not just between the Earth and Moon, not just between the Earth and the Sun. We choose a reference point that's at infinity. The idea being that if you are far enough away from all masses, the forces of gravity on you will be zero because there's no mass close to you. Right? If the expression is m1 times m2 times g over r squared, if you can make r infinitely big, then no object can apply a force to you. So we use a reference point for potential energy at infinity because that's something that could be common to all objects in the universe. And we use that as our reference level. That becomes a true reference, unlike a relative reference. Now this would work for roller coasters and such, but the problem is that force of gravity is constant enough near the surface of the Earth that we don't have to use this complicated way of thinking of energy. But this is how you would have to think about dealing with energy if you wanted to, say, go into orbit and figure out how much fuel it would take to do so. Or go from here to the moon and figure out how much fuel you would have to have with you to go there and make it back. This is how you calculate the amount of energy you need to bring with you, or the amount of energy you need to expend. When it comes to trying to go someplace, you guys realize that, yeah, you can calculate how fast the rocket is going, but how much fuel does it take to get the rocket to that speed? And maybe to maintain that speed all the way to where you're needing to go. It's not as obvious as it seems, but this is how you do real rocket science, is by dealing with how much energy there is. We know how much energy is contained in the types of fuels we use for rockets. So the question is, how do we calculate the actual amount of potential energy we have? When we're trying to say, I'm on the Earth right now, how much potential energy do I have relative to a point infinitely far away? So what we're going to do is we're going to calculate the amount of work done. in dragging one of you from the earth to a point infinitely far away. So we're going to say how much work is necessary to go from the surface of the earth to a point infinitely far away. And we'll use that as our amount of potential energy. Now, the truth is, we're talking about the amount of work necessary to take you and move you to infinity. The way this is done in your textbook is it talks about how much work is necessary to put you at infinity and bring you to the earth. Well, I'm going to talk about it in the opposite context, but only because I think it's easier to understand when I talk about it in the opposite context. Mostly because you can probably get behind the idea that you could start on the earth and be dragged away from it. It's hard to get the idea that you started infinitely far away and fell into the earth. You guys follow me? So we're going to start by the idea of how much energy does it take to get you off the earth, and truly off the earth, right? This would be not just going to the moon. This would be to get you off the earth so that you are no longer influenced by Earth's gravity. Now, this is kind of a thought experiment that's fictitious, because the truth is, as soon as you get yourselves off the earth, you're stuck in Jupiter's gravity or the sun's gravity or something else's gravity. There's a lot of things around here that all have mass. So if you really wanted to leave the earth, this wouldn't be enough. You would also have to take into account all the other things that would be acting on you. Does that make sense? We're just talking about the earth for this particular activity. And part of that's because we're talking about how much energy we have when we're on the earth. What is our potential energy when we're considering this comparison? Also, and I want to be really clear about this, I think most of you guys have the wrong idea about what infinity is. And that's not something I'm going to easily break. Infinity is not a number. And you guys, I think, have been told that it's kind of a number. It's not. Infinity is an idea. It's a concept. You use infinity most of the time in situations in which you're calculating the limit, right? The limit is something approached infinity. We tend to use infinity a lot in physics to talk about situations in which some number happens to be either very big or very small compared to another number. And we say the word infinity and throw it around a lot. It's a concept. It's not a number, so you can't treat it just like a number. We treat it like a concept. Does everybody understand that a little different? So, all right, so let's talk about you. We're taking you from the earth and putting you someplace infinitely far away. I think it should be pretty clear that we're moving you this way, and I'm going to put that as dr, because we're moving you along a radial. So the first thing I will change is, in my equation for work, the dx represents an incremental change in position, but that change in position is along a radial that leads away from the earth to some point infinitely far away. I'm also going to recognize that the force of gravity is towards the earth, making a dot product that's going to produce a negative sign. That's okay too. So I'll have negative mass of u, mass of the earth, g over r squared. Now, r is implicit in the formula. It is the distance from the center of the earth to where you happen to be. So when we're talking about r, I want to be kind of clear that we're going from the center of the earth to you, which is why we don't start at 0. We start at the surface of the earth because we can't get to the center of the earth. Does that make sense? That's why we're not starting from 0. All right. This part's not tough. The rest of this is just going to be the mathematics to come with how much work is done. So let's do the first part of this. Some of these things that are in our expression don't change as you go from the earth to infinity, like the mass of u and the mass of the earth and stuff like in g. Those things don't change. So I can pull all of those outside of the integral symbol. And I'm left with just 1 over r squared dr. Now this is a polynomial, and so it's going to be relatively easy to take the antiderivative of the polynomial, but I think as a polynomial goes, it looks better if we write it more like a polynomial. So I think all of you know this, but somebody in first period questioned it, so I want to be clear. You can take something that's in the denominator and move it to the numerator, but it does involve you changing its exponent to be negative. Right, you guys know that? You can do it in both directions. But that makes it look more like a polynomial for us. And for any polynomial, we're going to do the antiderivative. We're going to add 1 to the integral and then divide by the new, add 1 to the exponent and then divide by the new exponent. So for this one, I'm going to have r to the negative 1 power divided by negative 1. All good? All right. One more step, and that's just to plug in my limits of integration. And that's going to be negative 1 over infinity minus negative 1 over RE. So the work done, 1 over a number that's getting really big is going to be 0. So this term becomes 0. Right, the limit as that number approaches infinity. You guys good with that? All right. So that just leaves me with negative times negative makes positive plus the other negative there. So I'll have negative mass of U, mass of Earth, G over RE. Now, this part's going to be weird, so bear with me, all right? This says the work done in getting you off the Earth is negative, which means your change in potential energy in going from the Earth to infinity appears positive. Right, this is what it takes to get you infinitely far away from the Earth. Now, you're all writing that down, but this is where you need to stop for a second and hear what I have to say. We're all trapped on the Earth, meaning this is the amount of energy it takes just to get you off the Earth, which means when we look at how much actual energy, potential energy you have, this is a positive number to get you off the Earth, which means when you are on the Earth, your actual amount of potential energy is negative. We say that you are trapped in a gravity well, that to get you off requires energy just to bring you to 0, to bring you to the reference level. So what we say is gravitational potential energy is negative. When you're on the Earth, if I'd done the reverse of this and had you fallen from infinity, just give you a little nudge to get you started, and you would have fallen to the Earth, we would have calculated that the energy to get to the surface of the Earth from infinity would work out to be negative. So we state that your amount of gravitational potential energy is considered a negative amount. And that for you to get off of something, you have to bring your energy to 0. So, like I said, it's kind of like saying you're trapped inside a well. And the well is at the reference level. If you're down here at the bottom of the well, and I tell you the reference level is here, it's like having negative potential energy because you're below the reference level. That's how we describe the potential energy that you have when you're trapped on an object like the Earth or the Moon or any other planet, that it takes energy to get you to 0. Now, you may not understand that, but this is how we define gravitational potential energy when dealing with things that are astronomical. We say that you have negative potential energy. In fact, what we're going to find out is that unless you are escaping something, you will always have negative potential energy. In fact, consider this for just a moment. What would it take to get you off the planet? I mean, if I wanted to send you off the planet to a place infinitely far away so that you would leave the planet and just make it to this point without any velocity at all. You'd be at a place where you're not experiencing any gravity and you just come to rest at that point. Well, if I wanted that to happen, I would have to add kinetic energy to your potential energy. and try and bring your energy to 0. If I do that, I would be basically giving you enough kinetic energy when you're on the surface of the planet to just get you off the planet to a point where you are infinitely far away and then wouldn't be able to fall back. Right? Because you'd be at a point where there'd be the force of gravity on you would be 0. So we could calculate how much velocity you would have to leave the Earth. We call this the escape velocity. How much speed does it take to kick somebody off the planet and truly kick them off where they just can't come back? Which M is this one? You or the Earth? Yeah, we're sending you away. We're not sending the Earth away. Excellent. So, take a minute and tell me what the escape velocity is for the Earth. You'll need things, but I'm sure you remember them from first semester, like what the mass of the Earth is and what the gravitational constant is. I know you'll love that one because it's got 6, 7 in it. And you'll need the radius of the Earth too, because we start from the radius of the Earth. So I'm sure you remember these values. But in case you don't, they should be in your notes because you know things. So I hope you guys figured out that the mass of u doesn't matter in this expression. So the escape velocity is the same for any object you're trying to heave off the planet. And that you're just doing a little bit of algebra. Yeah? Well, that'll be a problem. So did you get about 11,000? Now, you guys are capable people, so you have an idea of the escape velocity now, but you also have another skill, and I need you to practice that skill. So do you remember us calculating an orbit? Sorry, but we did this already. I shouldn't have to reteach. So how fast is a standard low Earth orbit? I want you to calculate it again. And if you don't remember how to do that, I will give you one hint that an object in low Earth orbit doesn't have to get off the planet. It has to be traveling in a circle around the planet. So the net force on that object has to equal MAC. This is not much work. You should be able to do this with the information here. So you have the escape velocity. I want you to calculate a low Earth orbit. Assume that we are in low Earth orbit, which means that it's not much above just the simple surface of the Earth. So we'll use the radius of the Earth for our low Earth orbit. So hurry. Did we find it? It is significantly smaller than the escape velocity. Got 7906. So way slower, but still pretty fast. Now, if you're still typing into your calculator, that's a waste of your time. Your resources are more valuable than that. You should practice, of course, but the M's here are the mass of u. They cancel out. One of the R's cancels out. And you get a very similar expression, just that the 2 is gone. Right? You see that pretty clearly? Go ahead.
I did it wrong, and instead of putting...
Not a mistake. I mean, it is. But if you're near the surface of the Earth, your acceleration is g. Right? So that's why that worked. It wouldn't work if we were talking about the International Space Station, where the acceleration would be less. But at the surface of the Earth, you remember calculating the acceleration of gravity near a planet was just putting in the same orbital parameters being near the surface of a planet, right? And that's how you calculated the acceleration of gravity near the surface of the Earth. This was the first thing we did when we talked about this formula for the force of gravity. So, yeah, I wouldn't have put in mg. I would have wanted you to do this, especially if I'd asked for, say, the moon or something like that. But that's why that worked for you. But again, you need to know that that is a consequence, not a result. Does that make sense? Now, there's one more place I want to go here. So I want to just talk about the orbit for just a minute longer. An orbit is going to be the combination of an object's potential energy and its kinetic energy. So we talk about the energy of an orbit. It's going to be the combination of those two factors. Orbits conserve energy. Circular orbits, it's easy to see why, but orbits conserve energy. And part of the reason why it's easy to see from a circular orbit is because the only force acting on the system is the force of gravity, which acts towards the center. Because of that, this force doesn't do any work, and so the energy of the system stays constant. Now, it's going to be a little weirder when we talk about elliptical orbits, where the force isn't always towards the center. The force is sometimes contributing to an increase and a decrease in velocity. But it's still a conservative force, and because it's a conservative force, an object's kinetic energy and potential energy might change in an elliptical orbit, but the total energy stays the same. Now, in a circular orbit, these two stay the same the whole time, because your speed is constant in a circular orbit, and your distance away from the planet is constant. But it should be very, very clear, and if it's not, it should go into your notes. This is going to be negative. It will have to be negative as a consequence of how we calculate gravitational potential energy. So even though you're going 7,900 meters per second, you're not going the escape velocity, which would bring those two things to zero. So this, an energy of an orbit, will always be a negative number. Always. And we can kind of prove that right now. If we take a look at just what you did, the gravitational potential energy will be minus mass of U, mass of Earth, G over radius of Earth squared. The kinetic energy is going to be 1/2 mass of U V squared. Now you just calculated V a second ago, but let's go ahead and sub it in, not the number, but sub in the expression that you have, which is going to be 1/2 times the mass of U times V squared, which is mass of Earth, G over radius of Earth squared. Right? You squared that square root value right over here someplace, say. Now I'm just taking this and subbing it in for V squared. Sorry, that's not equals, that's plus. Now if you look closely at this, I'm just going to rewrite it. For this circular orbit, is it clear this has to be negative? Do you see why? I mean, this has a 2 in the denominator, so this number is going to be less than this number, but this number is negative. So although this is a smaller number, this is a bigger negative number, making this whole term always negative. Objects in orbit are just as trapped as objects on the surface. They're still stuck in the gravitational well and can't escape.